Hello, today I'm going to talk about the basic unmanned aerial system terminology and convention. So this is the continue of the last lecture that we had. So if you remember last time we talked about the configurations of the aircraft and also including the drones based on the regime of the flow or based on their payload or their sizes or the other criteria. So today we are going to talk about the other terminologies, which is mainly about the geometry or some other types of configuration, like the configuration of the tails or other components of the aerial system. So in the aircraft design requirements, there are different parts that we need to consider whenever we want to design a UAV or a manned or unmanned aircraft. So the first one is a mission. So we need to know what are our missions that our drone is supposed to do and what should be the performance of our mission. It means that how long flight our system need to perform, and stability and control. There are other criteria which they are important. So for example, if you want to design an airplane or a drone with a high actually stability, it means that we need to consider some component during the design process. Control is another criteria which is important. We have the cost. I mean, the expenses that we are actually considering in order to design or manufacture a system is so important. Being operational is important. Time of the manufacturing or the design is also important, and the manufacturing process and the material that we are using. So these are the total aircraft design requirements that we need to consider. So after considering this requirement, we will actually identify the major components of our system, which requires to satisfy these design requirements that we have here, including mission, performance, stability, control, cost, operational time, and manufacturing. So here we need to identify the component like the wing configuration, what is going to be shape of our wing, or what is the aspect ratio of our wing. We need to also define the tail configuration, what is going to be shape of our tail, the engine configuration, the type of our propulsion system or engines, the landing gear configuration. So for example, if you remember that we talked in the previous lecture, we said that the landing gears on the sea-based airplanes are different with the land-based. So for example, if our airplane is supposed to land over the water, surface of the water, the type of the landing gears are different with the aircrafts or drone, which are supposed to land over the land. So structural configuration is also important, and the mechanism configuration that we will talk about one by one of these major components in future. So after having this, we will have the configuration optimization. So for example, what should be the shape of the wing, how should be the type of the tail. We have a varieties of tails that we will discuss later. Where should be the position of the engine, or what should be the type of the landing gear, how should be the structure. So we will have all of those components. If we gather all of them and integrate them to one airplane or one aerial object, so then we can start our configuration optimization. So for example, here it means that this type of tail, it doesn't work with this design, so we need to change the tail. So after this configuration optimization, we need to do the aircraft optimum configuration. So we will have the optimization for the whole aerial system. So here there are these major components and their functionality and the primary function and the area that their influences, that we need to consider once we want to design each one of these components. The first one is the fuselage, and we know the fuselage, which is the body of our aerial system, is responsible to carry the payload. So this is the main reason that some airplanes, like cargo airplanes, they have a big fuselage. Or for example, if you remember last time we talked about the fixed-wing micro aerial vehicle drone, which are mainly consisted of flying wing So here the fuselage is so important to be able to carry the electronic equipment like battery, speed controller, or other component. So the major areas of influence for the fuselage is going to be aircraft performance, the longitudinal stability, and the lateral stability, and also cost. So for example, if you design a cargo airplane, the cost of the design of the fuselage is so high. And also the fuselage can affect in the longitudinal and the lateral stabilities, where actually the position of the wing on the fuselage or the shape of the fuselage can affect on those type of stabilities and also the aircraft performance. So the next component is the wing. As we discussed earlier, the wing is responsible to generate the aerodynamic forces and mainly lift. So the wing is responsible to provide enough force to keep our aerial system in the sky, which can compensate the weight and keep our airplane in the sky. So the wing is affecting on aircraft performance and also the lateral stability. We have the horizontal tail, which is for the longitudinal stability, and it also affects in the longitudinal trim and control. We have the vertical tail of our airplane, which is used for the directional stability and directional and effects and directional trim and control, and also the stilts property of our airplane. We have the engine, which the engine is responsible to generate the thrust force that our airplane can compensate actually the drag force, which is the force from the resistance of the air once our object is moving in the air, and eventually can again affect on aircraft performance in the stilts property, in the cost and control. So why an engine can be important and can affect on the stilts property. So as we discussed earlier, in the previous lecture, we had different types of the engines in propulsion system. So you know that one of the concepts that airplane, the rudder can catch the airplane is their configuration, and also there are the thermal effects. So we know the engines, they are using the fossil fuels or type of the other fuels that they will be converted the fuel to the energy. So this would add some heat, it generates some heat around the engines, which there are some type of the thermal radars that they can recognize this airplane. The landing gear is also another parameter which is responsible to facilitate takeoff and landing, and it can actually affect on aircraft performance, the stilts property, and the cost. And eventually we have the control surfaces. So the control surfaces there are varieties of control surfaces, including the aileron, elevator, and rudder, so that they are on wings, on the tail, horizontal or vertical tails, and they are more for control the aerial object in 3 different axes, and also it can affect in the maneuverability and the cost of our actually design. So as if you remember, we said that airplane can be classified depending on the number of the wings. So today we are going to talk about the wings and the geometry of the wing. So if you look at here, there are airplanes can be divided based on the number of the wings. So for example, we can have a monoplane like this airplane, which has just one single wing. We can have a biplane configuration, which they have 2 wings at the top of each other. Or as I said, these are the old concept that airplane was supposed to generate extra lift for flight. And we have the triplane, which they are similar to 2 plane, but instead of 2, we have 3 wings at the top of each other. And usually one of the wings is underneath of the fuselage, the other one is at the top, the other one is called upper wing. Also, the wing location is so important. For example, the wing should be at the bottom side of our aerial object or drone, at the middle of the fuselage, at the top of that, or the parasol wing. So there are 4 categories that we can see here. The first one is a low wing, which is at the bottom side of the fuselage. The second one is a mid wing, which is at the middle of the fuselage. the height wing, it's at the top of the fuselage, and the parasol wing, which is called the higher wings. It means that there is a gap between the wing and the fuselage, and the fuselage usually connect to wing, not directly, but through some spars and some rods, as we can see here. So another way of the configurations are the shape of the wing, which is called planform, and it is so important once we want to design a drone, a fixing drone, or an airplane, or any aerial object which is fixed wing. It means that it has a wing which is not flapping, which is not rotating, is just fixed. So there are varieties of wing types or wing shapes, which includes the rectangular wing shape, as we can see here in this model. We can have the tapered wing, as we can see here. So here, in the difference between the rectangular and the tapered is that their chord lengths for the rectangle, for the root chord, is equal to the tip chord, but in the tapered, the tip chord usually is smaller than the root chord, as we can see here. We can also have the delta configuration. This is an example that you can see here. We can have the swept back wing is exactly like this. So if we compare this wing with the swept and this tapered wing, we will see that there is an angle between the leading edge of our wing with the horizontal axis. So we have swept forward. So this is an example of sweep back. As you can see here, the wings are in the backward. We can also have the sweep forward that I can show you here, an example of the swept forward airplane. So if we compare the sweep back and sweep forward, we'll see that these wings are backward, but this is on swept forward. We can also have the elliptical shape, that the wing shape is like an ellipse. So this is an example that we can see, and usually these wings, they have different characteristics than the rectangular wing shapes. They have some advantage and disadvantage that we will talk more detail about them later. So the airplanes usually, or drones, in order to control in the pitch, roll, yaw axis, these are the three main axes that we will discuss about them in future. So our airplane should be stable in these three different axes. It means that, for example, if your airplane is flying horizontally, so weight should be equal to weight. But there are some flight modes that our airplane cannot be actually fly easily, and their flight modes are different. So for example, during takeoff or landing. So this is the reason that, or through the loitering flight or turning, this is the time that our airplane should have some control surfaces. So there are varieties of control surfaces that we will talk about them later on. But here, one type of the control surfaces are high lift devices. There are some criteria, or sometimes we need to get extra lift. So for example, imagine that your airplane is flying in the low dense air. It needs to generate extra lift in order to compensate the weight in the sky. So this is the main reason that airplane can create, use the high lift devices. So the high lift devices are plain flap. It can be a split flap. It can be a slotted flap. It can be Kruger flap. It can be double slotted flap. They can be triple slotted flap, leading edge flap, and leading edge slot. That we have their shapes here. So for example, the plain flap, if we look at here, this part of the wing, as you can see here, which is an example of this one here, this is just moving upward and downward. So this is called plain flap. And this is a basic section for sure. And the next one is a split flap. It means that the flap is the extra part which is connected to the trailing edge of the section of our wing, which is an airfoil. So this part is an extra part that it is added to the wing. We can have a slotted flap. It means a part of the wing is separated, another part is constant. This is called separated flap. We have Fowler flap. It means that this is moving from here to here. So in this case, you are changing the size of your, the core length of your wing, and we can have a slotted Fowler flap. So as you can see, it's composed of two different parts, and both are movable. We also have this a slat or a slot and a slat, which they are usually in the leading edge. So this is a fixed slot, as we can see here. This is a leading edge slat which is moving in this direction, and we usually see them in the aircrafts when they are flying. This is a Kruger flap, as you can see here. Once you want to increase the drag or during the landing, this part of airplane usually gets open, and we have the leading edge droop. So this is a part that you can change the leading edge of the wing of your plane. So we will talk about the geometry. So these are all called airfoil, which is the section of the wing which they are responsible to generate the aerodynamic forces. So once we get to the aerodynamic analysis, in this course, I am going to discuss more details about this type of the shape, which is a cross section of our wing. We also have the plain flap, as you can see here, a slotted flap, Fowler flap, and a split flap. As you can see, this part, it is going to be this one. So these are some examples of the high lift devices that I wanted to show you, but this is actually out of scope of this course, because we want to design a drone, right? We want to design an unmanned aerial vehicle or UAV or UAS, and these are for more passenger aircraft. But this is just for your information about the different devices that can be applied to make the airplanes. So the high lift devices that we discussed, including the plane flap, you can see them, that this is a plane flap which is changing, and it seems that it's in the wing and near the aileron. This part is called aileron, and it's mainly used for actually the roll control, and your airplane can turn with just moving this aileron. So here we also have the split flap, as you can see here. Once the airplane wants to actually take off, so they can open this, or during the landing, it's called a split flap. We have the slotted flap that shows that this is a part which is slotted from the rest of the flap. We have the Kruger flap, which is in the leading edge of the airplane. This is double slotted flap. As you can see here, this is flap which is composed of two parts, and this is the reason that it's called double. We have triple slotted flap, which is composed of three parts. So if I want to show you here, this is 1, 2, and 3. So 1, 2, and 3. So these are movable objects that can actually help in the generated lift during the takeoff or landing. So these are another example. So we have the leading edge flap as well. So these are some trailing edge and leading edge. So this is a firefighter. As you can see here, this is a moving part at the leading edge of the wing, which is called leading edge flap. And also have trailing edge flap here. And this is a horizontal tail and a rudder, which is more for actually lateral control. So this is another example of the leading edge flap that we can see here in order to change the lift distribution. So this is a fixed slot, this is a movable slot, leading edge slot, and leading edge cuff. So as we discussed, these are not used usually in the drones, specifically on the micro drones that our main objectives in this course are design of the fixed wing UAVs or MAVs, which is stand for unmanned or micro aerial vehicles. So going back to next slide, aircraft, they can change their configuration sometimes. So for example, they can change the sweep angle and the sweep configuration, as I said, that these wings are sweep back or sweep forward. So if the sweep is movable, it can be fixed or it can be the variable sweep. So for example, if you look at this airplane, this sweep angle is constant. So our wing is constant and it's fixed. So this is the reason that it's called fixed wing sweep. Well, but also if you look at this concept, we will see that the shape of the wing and the angle is changing and the wings can be folded. In order to get speed or order to fly faster, the airplane usually change their sweep angle, which is called variable sweep. This can actually change the type of the airplanes that we have. So for example, if they want to get speed, they increase their sweep back angle in order to reduce the surface area to get more speed and reduce the drag. And sometimes, or to go faster actually, and sometimes once they want to glide or fly in the actually longer time, more stable, so they have a lower sweep angle as this dashed shape of the wings that we see here. So we will see also the sweep angle in the nature. There are a bunch of birds like the eagles. Once they want to catch some fish under the water, they fold their wings like that. So these are they doing a sweep back in order to fly. So here again, the aircraft wings can be actually classified based on the shape into the fixing and the morphing wing. Fixed wing, that means that the wing is totally fixed, and the morphing means that you have change in the sweep angle or in the shape of your airfoil or in the shape of the wing, exactly like these two concepts that we see here. So if you look at the feathers of the birds, generally the feathers are, the wings of the birds are consist of two layers of the feathers. There are primary and the secondary feathers. So this part of the wing usually has the higher, is more solid and is responsible to generate lift, has less flexibility, but this part are actually having more, they're more flexible and they are responsible to generate the thrust during the flight. So if you look at the shape of the wing of the birds, so this wing shape is consisted of the folding part and the constant part. So if you look at here, usually birds, their wing has a hand and has an arm. So here, this part of the wing, it can be easily folded in such a way to have a morphing configuration. And this is something exactly we see here. This is one of the design aircraft by NASA, which the material used and structure in such a way that this airplane can change. It doesn't use the contour surfaces, and it can have a morphing capabilities, and use with changing the structure of the wing can actually have different control. So airplanes also can be classified based on the structural configuration. We have the cantilever configuration. So this is an example of the full cantilever structure, where the wing is attached to the fuselage at the top or bottom side of the airplane. So as we can see here, if you consider this one as a fix, this is just a cantilever beam. So this is like a cantilever beam. We can also have the strut braced configurations, including the ferret and unferret. So here, these are other examples that we can see here. So for example, this is wire braced biplane, and here is a long struts brace with the jury struts. And this is an example of the semi-cantilever wings. So based on these extra parts that you have, you can have cantilever, or you can have the strut braced wings. So this is an example of the strut braced wings. So if you compare this wing, there is no any struts here, but here you have this extra part which are keeping your wing attached to the body. So this is another configuration of the wing that you have. So the aircraft configurations alternatives, I mean, can be changed based on the tail configuration. There are varieties of the tail shapes based on their location and also based on the configuration. So we can divide them to the aft or forward tails. So it can be aft conventional tail like this. So this is a T-shaped tail, which is in the aft or back side of the fuselage, and it has a conventional shape. We can have the canard or foreplane tail, which the tail is actually in the front of the fuselage. So the difference between this airplane and this one is that this one tail is in the aft, but this one is in the front. And also sometimes we can have three surfaces. We can have the combination of the aft and the canard tail. So here we can see a conventional tail at the back of the wing. Here we have the wing, which is responsible to generate lift. We also have this part, which is foreplane or canard tail. So here we have three surfaces, and this is the main reason that we classify them as three surfaces. So there are varieties of the wing shapes for airplanes and drones, and I'm going to show you some example of this tail. So we can have the conventional tail, as you can see here, that once I say tail is a combination of the vertical and horizontal tail. So if you look at here, this is a vertical tail and horizontal tail in a very simple way, which is called conventional tail. The next one is a V-tail tail. The tail is like a V shape. This is an example of the V-tail. We also have the inverted V-tail. So it's something like this. Is an inverted V. We can have the T-tail. Our tail is like a T. We can have the H-tail. Our wing is like H. So I don't have any picture here, but if I want to show you how this works, is a tail like this. So for example, something like this, come boom mounted, but it can be as H-tail, H-shaped tail. We can have inverted U, which the tail is like a U. So this is an example that for inverted U. So this is a shape like that. We can have the cruciform tail, which is something like that. This is a horizontal tail, and this one is vertical tail. So in the cruciform tail, the vertical tail is not at the top, which become like the T-tail, or it's not the bottom side, which will become like a conventional tail. So it's somewhere in the middle. This is the reason it's called cruciform tail. We have the dual tail. So we can have actually the triple tail. You have three tails, is like this. This is 1, 2, and 3. It means the vertical tails are 3. Inverted Y tail, this is another one. This is an example of the Y tail. If I want to show you, this is a Y tail, and the inverted Y tail is going to be like this. We can have a twin tail. So you have two vertical tail at the top of the horizontal tail. We can have high boom tail. So this is one of the example of high boom tail. So this is an example that they are connected to the booms. And we can have the ring tail because a circular tail. So these are the configuration of the tail that generally we have them on the airplanes or on the drones. So here I have some pictures of varieties of tails that they have been used in the airplanes or in drones. So for example, this is an example of the conventional tail. This is a V tail. This is an inverted V. This is a T. This is inverted U, is like a U. This is a cruciform tail. This is a dual tail, triple tail. We have inverted Y, as you can see here in the shape. we have the twin tail like this, and we have the high boom tail, which the vertical tail is at the top of the two, or horizontal tail is at the top of the two vertical tail. And we have eventually ring tail, which is a circular tail. So these are the varieties of the tail shapes that we have on drones or airplanes. If you look at the nature, we will always get inspiration. So there are varieties of the tail shapes in the nature. So for example, if you look at the birds like these hawks or the owl, you'll see that how their tail is wide, for example, compared to this bird. So the tail of the birds can be forked, can be square, can be notched, can be rounded, can be double, can be fan, can be wedge, and can be pointed. So these are the different shapes that we can see in the nature, and we can get inspiration in order to design some tail for drones. So as an example, I am going to show you here a flapping wing drones that we have. So as you can see here, this shape of the tail is like a fan shape, as we saw in the lecture. So this is a bird-shaped tail, which is able to go up and down in order to act for going up or down, and also it can rotate to the left and right in order to turn this flapping wing drone. So going back to the presentation, there are some species in the nature which the tail has actually act like the wing, like the butterfly. So they have two parts in their wings. So this can be their wings, and this part can be considered as a tail or as a wing. There are some other species like the dragonflies, which they don't have any tail like this. So the tail is acting like the stabilizer. So this dragonfly have 13 degrees of freedom. So the 12 degrees of freedom is coming from the wings, and 1 degree of freedom is coming from this tail, which is a different with the tail of the birds or other insects. So the tail configuration can be actually categorized based on their attachment mechanism. So for example, we can have a fixed tail. So this is a vertical and horizontal tail. They are both fixed, and this is the reason it's called fixed tail. But we can also have the moving tail, as we can see here. This is a tail. These are the tail, horizontal tail, and these are the vertical tail, which they can move. And we have the adjustable tail. So for example, it can go up or can go down. You can change the angle of attack, as we can see here in this area or this region. So this part can actually go down or go up, or it can change the angle like this. And this is called adjustable tail. So now the another configuration was based on the propulsion system. We talked about the engine types and different types of the propulsion mechanisms. So this is an example of engine types airplane that we can see here. We can have the human powered, like this concept. The guy is in the bike, and it's using its power in order to create the thrust and eventually get lift. These are the human power airplanes. You can have solar power, that you are using the solar panel at the top of the wing. This airplane has been designed by NASA, and this is generating lift, and it's a solar base. We can have the piston prop or piston propeller. So you have a piston and a propeller which create the thrust force. We can have a turboprop. This is an example of the turboprop. We can also have the turbofan. This is an example of the turbofan airplane. We can have a turbojet. This is an example of the turbojets, and eventually we can have their rockets. So this is one of the example of the maybe hypersonic airplanes that they're using the rocket engine in order to get thrust. So they are so fast, and they're usually flying in the high Mach number. So regarding their propulsion system, The airplane also can be categorized based on the location of the engines. Is it in the back or is it in the front of the airplane? So this is so important once you want to consider the stability points of view for our design. So the propeller or the engine can be pusher or tractor. So this is an example of the pusher. Usually the pusher, they are in the back side of the airplane. As you can see here, they are pushing the airplane forward. And we can have tractor, which they are in the front of the wing. The structure is so important that how you are adjusting the weight and how you want to consider the efficiency of your propulsion system during the design. These are some criteria that they are important once we want to select where we should put our engines. Is it in front? Is it in the back? Is it in the middle? Where should be? Should be pusher or tractor. So these are some concepts that before designing in any unmanned aerial system or manned aerial system, we need to consider. So based on the number of the engines and engines locations, the aircraft configuration also can change. So for example, if we look at here, we can have a single engine as this concept. We can have twin engine like this airplane, which has two engines here. We can have tri-engine with the airplanes is using the three engines. So this is an example of the three-engine airplane. We can have four engines or multi-engine. So there's are varieties of the configurations of the airplane based on the number of the engines, depend on the weight, depend on the payload that airplane needs to carry. So we have a variety of configuration for our airplane based on the number of engines. The engine location is another parameter which is important. So for example, it can be in front of the nose. This is an example that we will see here. The engine is near the nose of the airplane as this concept. They can be inside the fuselage. So this is an example where the engines are inside of the fuselage. They can be inside of the wing. This is another example where the engines are inside of the wing. They can be at the top of the wing. They can be at the under of the wing. They can be inside the vertical tail. They can be size of the fuselage at the aft section. So they are attached to the fuselage, but at the end, and eventually they can be at the top of the fuselage. So these are different categories of the airplanes based on their engine location. So based on their landing gears, also we can have a different configurations of the airplanes. So the landing gear mechanism can be fixed, can be fair, and can be unfair. So for example, fair and unfair can be that they can actually fold themselves. So here, this is an example of the fixed landing gears. And these are some example of the retractable and the partially retractable landing gear. So if you look at this is a landing gear that eventually goes inside of the fuselage and is totally retractable. And also it can be the partial. It means that some part can be actually retractable and a part is not retractable. I mean, a part is fixed and part is fair. So the landing gear configuration, there are varieties of the configuration. We can have the tri-cycle or nose gear. There is a gear near the nose and there is a landing gear here. This is the reason it's called tri-cycle. We can have the tail gear. This is a tail gear. This is a tail of the airplane. There is a gear here and your landing gear is in front of your wing. We can have actually landing gear, I mean, aircraft without landing gears, like gliders that they don't have landing gears, is like this. We can have the bicycle landing gears. So if I want to show you, this is an example of the bicycle landing gear, that you have two pair of the landing gear in each side, which is called tandem landing gear. We can have a multi-wheel. This is actually can be considered as a multi-wheel, and this is actually a tandem, is a bicycle or tandem landing gear. So this is a tandem and this is a multi-wheel, as you can see in these concepts. Or here we can have the float equipped landing gears. So these are the landing gears that they can land over the water like this, or like this concept. We can have the removable landing gear, the landing gear that you can remove them, and usually this happens on the drone. So this is an example of the removable landing gear. So we can easily remove these parts. And as I said, this is usually mainly for drones. So we can have a configurations for landing gear based on the runway. So the runway is one of the interesting criteria that eventually would affect during the design process. So for example, there are some land-based runway that we can see in the airports, and they are in the land. These are called land-based. They can be sea-based, is exactly like this concept. They are near sea and they are sea-based. They are amphibians. It means that they are in the sea or in the land or over the water. So these are amphibian runway. We can have ship-based, is exactly like this concept that we can see. And we can have the shoulder-based UAV, which they are more hand-launched, and we are launching the aircrafts in order to get the speed to be able to take off. So these are the landing gear configuration based on the runway. We also have the fuselage configuration. If you remember, we said that the main reason to have the fuselage in the drone is that we want to put the components inside of that, or it can be cargo, it can be passenger, it can be any type of sensor, batteries, or different other parts that they are used on, specifically on drones. So, but the fuselage configuration is composed of the door. There are two doors in the aircraft, one for cabin and one for cockpit, which is, this is an example of the cockpit that we can see. And it's generally at the top of the airplane, and this is for the cabin. The design of this is so important actually in the aircraft industries, because they want to design something safe. The fuselage configuration can be classified based on the seats. The seats can be the tandem, it can be side by side, it can be N seats per row. So these are an example of N seats per row. This is an example of, let's say, side by side, and this is an example of maybe tandem configurations. So these are different shapes of the seats. So the pressure system is so important in the manned aircraft. So as I said, this is out of the scope of this course. I'm just giving you this information to actually improve or extend your knowledge about the aviation and aircraft industries, since you are using the same concepts on the drones and also in airplanes. So for the fuselage configuration, we can have the pressure system, pressurized cabins, pressurized hose, and unpressurized cabins. So the main reason having this ventilation system is that once the airplanes are flying at higher elevations, around 10,000 feet or 10,000 kilometers from the ground level or from the sea level, we have a big drop in the pressure. So in order to have enough pressure for the people or for the pilot or passengers, so we need to design a pressure system. So here we have the pressurized cabin, which actually can be used to coordinate the air inside for the ventilation inside of the airplane, and in the same time to have enough same pressure in the ground level. So if you look at here, this is an example that we have the engine air tank, which the flow of the air goes here to be heated. There is an air compressor here, which will mix unit, and it eventually goes to the different parts of the airplane. And here Then there are outer valves that you can open them to actually out the air. So these are different configurations for the pressure system of the airplanes. So there are varieties of techniques for material and for manufacturing of the airplane. So here we are classifying the airplanes based on the manufacture-related item configurations. So the first thing which is important is the material for the structure. We can have the metal like the aluminum or aerospace aluminums that is usually used to manufacture the airplane. We can have wood and fabric. As this example, this airplane is mainly made by wood. We can have the composite material, as we can see here, and we can have metal and composite material. Is a combination, different parts of the airplane you are making from different material. For example, this blue one is carbon fiber reinforced plastic. You can have a glass fiber reinforced plastic. You can have a quartz fiber reinforced plastic. This is actually the nose part of the airplane. The passenger aircraft, since they are going with the higher speed, they will try a very high values of the drag and the friction in the nose of this airplane. This is the reason that we are using a quartz fiber reinforced plastic. And we have the glass reinforced aluminum laminate. So this is a combination of the metal and the composite material in order to manufacture our aerial system. So the assembly technique is another way that we need to look at that. So once you want to design an airplane, so it can be kit form specifically for the drone. Is like a kit form like this. It can be semi-kit forms that they are modular. So I am going to show you an example of the semi-kit form of the airplane. For one of them that I have it here. So if you look at this concept, so this is an example of a drone, a fixed-wing drone with the semi-kit form. So I can easily open this part, as you can see here. So different parts can be opened, and you can see the inside and see that, for example, how different part or interior part of the drones looks like. So this is an example of the semi part. And you see that the wings are rotating like this, and so this is a semi-kit of the airplanes. So if we move to the actually the larger size airplanes, the story would be different. So this is using magnet in order to use for the nose or for the wing part of the plane. We can also have the modular. This is an example of the modular plane. It's usually mainly in the bigger airplanes, we will have the modular configuration, which they'll make the fuselage and they will attach the tail or the wing to the fuselage. There are also the other criteria which they are important to consider in the design of the airplanes. So let's go back to that slide. So as we said that this was the kit form, semi-kit, or the modular. This is an example of the modular that we discussed, that the airplanes are composed of the wings. They are making the wings separately, and they will make the engine separately, and then eventually they attach everything together to have more coherent airplane. So going to the next slide, there are different ways for manufacturing techniques and for metallic components. So they can use welding to, for example, it shows an example of the welding of the fuselage of an airplane. We can have the machining. This is an example, a type of the machining. We can have a casting. This is an example of the casting, and we can see how the sheet metal work, this is actually the casting. This is going to be machining, and this is the sheet metal work. So the guy is making an airplane. It seems that is a homemade airplane, but is using a sheet metal to create this fuselage. Or this is a machining, using machine to create this part of the aircraft. Or this is a casting that will make the mold and you can then eventually, once you have the mold, you will be able to make any shape that you want for different components of the airplane. Composite materials manufacturing technique is another way. There are varieties of the ways to create the composites. They can be hand layout. We can have the machine layout. We can have the weight layout. We can have the filament winding, resin transfer molding, pultrusion, and sandwich construction. So this shows an example of the hand layout where you have the fiber and the resin, and you will use those to create any shape that you want for your airplane. This shows an example of the hand layout that we can see, and it seems that they're fixing the airplane, and then they can paint it. We can have the machine layout. This is an example which machine is making the composite for the fuselage of the airplane. We can have the wet layout, which they put in the water. We can have the filament inside of the resin. We can have the filament winding. This is an example of the filament winding, and we can have the resin transfer molding. It means that they have their structure here, and these are the resins which you inject resin to inside of this mold in order to create any plate of the composite that we want to make. And this is one of the advanced methods, which is called pultrusion, or the sandwich construction of the composites. So the pultrusion, they are using this type of textiles to create any shape that they want. And the sandwich construction, they are using different layers of adhesive or the sheet in order to create a structure like this. So these are different methodologies that they are used to create or to manufacture the different structure of the wing of the airplanes. So the another configuration of the airplane is based on the control surfaces. There are the primary control surfaces, including the conventional, like the elevator, aileron, and rudder. So in order to show you this one again, I have the example here that if you look at here first in this shape, the aileron are the control surfaces which they are on the wing of the airplane. This is the wing, and these are the aileron. So in the aileron, one of them go up, the other goes down. It creates some roll, so your airplane will be able to have the roll stability. We have the elevator, which goes to the horizontal tail. Both of these, or it can be one piece, go up or down, and they are used if your airplane wants to go up or go down. We can have the rudder, which is a moving part of the vertical tail, is for yaw control. If we combine, if you have a flying wing, like this concept, here we have the combination of the aileron and elevator, and usually to rotate this, we need a servo motors that I will show you later on. What is the servo motors? And these are called elevons. Elevons they are the combination of the aileron and the elevator. So this was the elevon and the rudder. We can also have the aileron and rudder vator. So what is the rudder vator? So if you have the V formation tail, as you can see here, the rudder, which is for vertical tail, and elevator, which they are for horizontal tail, they will be combined, and this is called rudder vator, because the rudder vator is usually for a V-shape tail. And in the V shape, if we compose, so if I want to draw it here, if this is a V-shaped tail, right, is exactly like the shape that we have here. If we actually decompose the surface area, I will get a surface area here, and I get a vertical component here, right? So this part which is the projected surface area of the V shape, is called horizontal tail, and these vertical parts are vertical tail. Since you are combining these two and the contour surfaces, including the elevator and rudder, they will be combined. This is called rudder waiter. We can also have the flaperon, rudder and aileron. So these are the flaperon that they are extra part to contour surfaces, as actually they are acting like the high lift devices or for having more control. And we can also have the cross or plus sections. So these are some examples. Actually, I couldn't find any picture of this cross section, but what I guess is that if our tail be like this or our tails be like this, so this we can have a varieties of control surfaces. So there are also secondary control surfaces, including the high lift devices that we discussed already about them, including the flat, a slat, or a slot. We can have the spoiler, and we can have the tap. So the spoiler is actually on it can be on different parts of the contour surfaces. It can be on a vertical tail, or it can be on horizontal tail, or it can be on the wing. But the tap, or this part, which they are moving, this tap is this part, which is, so this is moving part, and this is an example of the tap, which it has a pivot point here, and a stabilizer is here. This is another extra part which is moving with the control surface. It's called tap. So these are other actually secondary control surfaces that we have. So now I want to show you these control surfaces and all the stuff that we discussed in two different types of airplane. So if I want to show you this airplane, this is consists of the fuselage, wing, booms, vertical tails, and the horizontal tail, right? This is a horizontal tail, vertical tail, boom, fuselage, and the wing. So now, if we consider this, I want to discuss that where is the location of the wing? Is it in the front, middle, or back bar? Again, where is the location of the wing? Is it the top, upper, down, or middle? Where is the type of the engine? Is it pusher or puller? What is the type of the tail? Is it going to be double boomed mounted tail, or H-shaped tail, or U-shaped tail? What is the shape of the tail? Where are the control surfaces? Here. So let's look at more closely. So this is a fuselage. The wing is connected at the end of the fuselage. So these are called booms. And this part, which is container of all electronics, as I showed you, and I can show you here, they are inside, including the batteries, speed controller, or other equipments. This is actually the fuselage, which is the container. So this wing is at the back of the fuselage, right? So, and it's at the top of the wing. It's not at the bottom side. It's not at the middle. It is just at the top. So it's top wing. So our propulsion system is using electrical motor and a propeller base, and it's pushing because this is pushing airplane. It's not in the front, right? It's not tractor, it's pusher. The shape of the tail is boom mounted twin tail. So we have two vertical tail, which they are responsible for lateral and directional stability. And we have the horizontal tail, which is mainly for longitudinal stability. So this is the shape of the tail that we have. And here, the another concept I want to talk about that is the whole structure. So you see the whole structure, we have these two booms, the distance from the tail to the wing. the position of the motor, the position of the wing, they are all influencing on the stability of this airplane. So now let's talk about the control surfaces. So these are called aileron, which are on the wing, and usually during the flight, one of them goes up, one of them goes down. So if you look at this scenario, this is up and this is down. So what would happen here, the lift distribution over the wing, this is something that I will show you in the software, it would be changed. So for example, lift in maybe this side of the airplane will be more than the lift in this side, because here or inverse. So then once the lift in this side is more than this side, so this would create a roll motion. So this is called roll motion. So these are the control surfaces called aileron. One of them go up, the other goes down. These are the vertical tail. This concept doesn't have rudder, but if you have a moving part here on the vertical tail, this is called rudder. So it means that if this moves like this, your airplane will be able to have the yaw control. This is the yaw control. Right? This was roll. This is yaw. And eventually we have this control surface, which is called elevator. So this is just are you just using one servo motor? This is called servo motor, which is moving this. And there's a mechanism here which creates this motion. And let's see if I get it closer. So this is going to be here. This is the servo motor in the black color that you can see here. So this is going upward and downward. Once the airplane wants to take off, you need to get extra lift or nose up your airplane. So this control surface goes up. I'll talk with more detail once you get to the design of this part. Goes up. So now in this case, when it's up, your airplane goes up. Once the airplane goes down, this goes down. It's like this, and your airplane will be landed. So this is an example of the configuration that we had. So this is one example of the commercialized, let's say, a fixed wing micro UAV, right? So this is an example that we have. Then I want to show you the other type of the fixed wing drones. So this is another example. This is a fixed wing UAV, which actually has a flying wing concept. Means that, see here, the body, the fuselage has been combined with the wing, and it has an airfoil shape, has very aerodynamic shape. And here, what would happen, we no longer have horizontal tail or those booms, right? So what we have here is just a wing. And this concept is called flying wing. Again, the wings are at the middle of my fuselage. As you can see here, the wings at the middle, the all wing. And I can actually separate them, and you can see that this is a modular airplane that we have it here. And so looking at here, this is the front part. So again, the motor is in the aft part of the plane. So this is a pusher, is not tractor. And the control surfaces are combined for the tail and for the wing. And this is the reason that since it's a flying wing, this is called elevon. Elevon is the combination of the elevator and aileron. So if one of them go up, the other one goes down, so you can have the roll control, right? If both, since you have two servo motors here, these are the servo motors. If both goes up, your airplane goes up and it will take off. If both goes down, your airplane gets down and it will be landed, and it can decrease the altitude. We also have two vertical tails here, and they can be as a vertical tail for lateral directional stability, and also can be considered as the wing tips that I showed you earlier, that the birds that are, once their wings are extended, they will fold the tips in such a way to create the winglets. So this can be as a winglet, or it can be as the vertical tail. So this is another example that I wanted to show you, and hopefully you have enjoyed this course. If you have any question, please reach me to my email. And so as I said, there are more information that I'm trying to cover in this class. I'm not going to ask, I mean, everything that I'm talking here, but it's just some of the information is just for to increase your knowledge about the aviations and the structure of the airplanes. And eventually, once we know about the bigger sizes, we can learn about these small drones that I showed you here, to sample of those. So this course is mainly about introduction to unmanned aerial system. We are talking about fixed wing design and the software that we will start. I mean, the next two lectures to actually work with that, you will learn how to design, model, and simulate and run different types of aerodynamic analysis in XFLR5, which is one of the commercialized software, free open source, that we'll talk about that in future. So please, if you have any question, please reach me in this email and contact me. If you want to have more information about drones, you can go to my website, and I have put all of the publication that I have in this area. So thank you, and I'll see you in the next